Hello guys, welcome to the Deep Learning Workshop series. My name is Sergi Adipraja, and I'll be going through one of the specialization tracks. I'll be talking about convolutional neural networks as a part of the computer vision specialization in the Deep Learning Workshop series. Hope you enjoyed several of the past workshop contents. And yeah, let me just go through a bit brief introduction about myself. So my name is Sergi Adipraja. Well, $50 for whoever can pronounce my name 5 times real fast. Joking. I'm a final year undergraduate in Nanyang Technological University at the time of speaking. Here's my GitHub account, and yeah, let's go through the contents of the workshop. So the first part will be think like a machine, right? So this is an introduction of the de facto machine learning project pipeline. So probably several of my colleagues have gone through this, but I'll also go through this so you guys have a bit of a refresher of what we are doing right now. So what is machine learning? So machine learning is approximating a relationship based on features. So take note that I'll be using the word features in a lot in this part of the workshop, so keep in mind that. So classification versus regression, I hope you guys have solid understanding on the inherent differences between these two machine learning tasks. So basically, classification is a machine learning task in which the output of your machine learning model would be a discrete output, whereas for regression, what you're doing is just approximating a real output. So basically, you are looking at data and then you're trying to approximate a relationship and hopefully generate new insights based on your machine learning model. So while classification and regression is a supervised learning problem, so this is one of the working example of a supervised learning problem. So first you have features. In the case for, let's say, fraud detection, or let's say a regression problem, you have features, definitely, and these features can come in the form as simple as tabular data, several numbers that dictate several features, several things about the samples that we are interested in. So let's say here is the crime ratio of a particular household. Not really crime, I'm not really sure that this can be one of the many examples. This can be the crime rate. This can be the age of the house, I'm not sure, and this will dictate the pricing of the house. So based on these features that we know that's interpretable, we are ought to predict a particular response variable, which is called the target variable. Excuse me. So yeah, so this is what happens in a during training in a machine learning problem. So this is a working example of a neural network. So this is going to be your input, this is going to be your output, expected output, and you can see as the training process as we go through the training process, you can see that the decision boundaries of our machine learning model is getting better and better. So this is basically in simple terms, you're learning from data and you're trying to approximate relationship between data. Then there's a very solid visualization of what's going on under the hood. So I'm sure you guys have heard of the term linear regression at this time of the workshop. So imagine here you have a response variable of y and you have a feature of x, and this is a simple linear relationship. But remember, in your secondary school you learn about linear equations. You have the gradient and you have the y-intercept. So a simple machine learning problem would probably be something along the lines of this, as simple as this, which is just trying to approximate what is the gradient, what is the m. In this case, you see here was the m, and what's the y-intercept or B of a particular linear relationship. So this is something as simple as that. So but you can see here, what you're trying to get here is actually the red line. Am I correct? So this is the red line, and as the red line gets more and more accurate and it fits the data better and better, you can see that the error or the loss here, the error is reducing. So essentially, remember in here we have a very nice visualization of what's going on. This is a more low-level visualization of what's going on during our training model, around our training process. Apologies for that. The error reduces over time as your model increases in accuracy, which is quite simple. But the algorithm here is in the error space, in this in the error function here, in the error space, you can see that you are actually just going down the hill. So you can, this based on calculus, you just go into, this is called gradient descent. I'm sure you guys have heard of this. It's one of the convex optimization optimization algorithm, or descending through based on the gradient. So yeah, in the case of a linear regression problem, so you have parameters to modify, right? So you have M and B, and you have a loss function to minimize, which is the value looking thing here, is the error function or the loss function, and you frame the problem as a minimization problem. So basically, machine learning is just a you can in simpler case, machine learning can be taught as a minimization problem. So at every time step, the dot moves closer and closer to the global minimum. And this algorithm, as I just mentioned, is called gradient descent. Okay. So this is an iterative process. So machine learning is basically an iterative process. So before moving on, I would like to go through several jargons that might be useful for you. So you have epochs, you have iteration, and you have batch size. So epochs, in the case of training, in the context of machine learning, epochs means how many times your model has seen the whole data. So yeah, an example, 100 epochs mean the CNN looks at the whole data set 100 times. So we went through the data set 100 times. Iteration means how many times it makes a gradient update. So you can see here, so it does quite a number of iterations because it went downhill several times. So how many times it makes a gradient update. Gradient update means you're stepping through the loss function space. And batch size is how many data that the model must see before one gradient update. So example here, he sees batch size of 40, means that every gradient update is calculated from 40 samples from your data. So he looks at the model here, in this case he sees 40 samples and then go down the hill, 40 samples and then go down the hill. It might not be an exact smooth, it might not go through the exact same trajectory that is being illustrated now. It might go through here, zigzag, and then ultimately it goes through the bottom. But approximately you can expect that the machine learning algorithm, the learning algorithm will converge to the local minimum. So generalizability is key. So here is 3 cases of the outcome of your machine learning algorithm. First is underfitting, where you can't really approximate a complex relationship between your data, and this is overfitting, which is you're over approximating, so you're learning too much in a way from your data. And this is just nice, right? So this is a perfect balance between underfitting and overfitting, or bias and variance in more legitimate terms. So, well, I think several of my colleagues have went through this validation method you go through your data set, and then you hold out several subset of the data set, call it the testing set, and then train on the training set, and then you approximate your model's relationship based on the testing set. So these are pretty much, I think this is quite straightforward, I would say. So yeah, that's a bit of a refresher of what is going on, what's machine learning. So you guys have a brief so you guys are mentally primed to go through this particular next chapter, which is the era of deep learning. So yeah, based on the tagline here, you have some more of them data. It's basically it portrays the data hungry nature of deep learning. So but then a lot of the data that it is within our within our scope is not structured. So remember last time that I went through the example of the tabular data. It's a form of a structured data. So it's easy to make sense. You just feed it to a learning algorithm with a standard machine learning algorithm, then voila, you're good to go. But then what happens if your data is not structured, which is in the case for most of our data that we have in in the internet, for example. So you have this particular data, which is tabular data, which is very structured, and then on the other hand you have unstructured data. You have images for in one hand, and you have audio data. You have audio spectrum that may constitute several degrees, higher degrees of complexity compared to this more structured data. So so that is where deep learning comes into play, where first machine learning is you are doing feature extraction, automatic feature extraction. Traditional machine learning algorithms, you do feature extraction, and you classify, and then boom, you have the output, which is the car or not car. So you have an image of a car, then you extract the features and then classify them to using a learning algorithm, then output whether it's a car or not the car. But in this case, for deep learning algorithms, you skip the part, you skip the feature extraction part because of the powerful feature extraction model that is embedded within the learning algorithm. So this is a graph that portrays the data hungry nature of deep learning algorithms. So deep learning algorithms are inherently more data hungry. It increases in its performance based on the amount of data that you feed into it. However, for traditional machine learning algorithms, it doesn't do so. You hit a plateau at some point. So this is what deep learning is. In the context of computer vision, so we have image features, and there are different ways to encode different semantic level, high level features on an image. So this, what do you see and how do you know it's a particular example of a cat, for example here. So you might see different things that might dictate a cat, right? They might dictate that it's an image of a cat. You see the ears and you see the eyes and you see whiskers, and boom, you know that's a cat. But then what the computer sees is just a sequence of numbers. It's just a sequence of random floating points. And the question is, how do you encode high-level semantic features on this image? So that's the question. How can you semanticize what the computer sees? So in this case, you only see, you can only see you see an image of a particular pedestrian, but how do you let the computer know that is an image of a pedestrian? So what you're going to have to do is to decompose the image into low-level features, such as gradients, histogram of oriented gradients in this example. See here, so something like this, and then you have edge detection to detect edges in a particular image. So here you see. So you see that it's an edge. See, there's an edge here, right? So in a way, you are trying to simplify or semanticize what the computer sees. Okay, but then those are low-level semantics. Edges and gradients. Where does the particular edges go? Right. That is called low-level semantics. But then, how do you encode higher-level semantics? For example, you have an image of a cat, right? You see whiskers, you see ears, right? That's high-level semantics. Then how do you encode high-level semantics on an image to a machine? And that's where convolutional neural networks comes into play. So I'm sure at this point you have heard of the term neural networks, and you are unfamiliar with the term of convolutional. So this is what a neural network looks like. So this simplest type of an artificial neural network, simply called is a multi-layer perceptron. In the case for digit recognition, so what you're going to just do is you have an input data, and then you have an input layer, and then boom, what you just do is just feed it to a feed-forward neural network, train it, and then you have a digit classifier. It works to a certain extent, and you might be surprised that the accuracy is quite big, around 90%. It works to a certain extent, but surely we can do better. So let's say you have a more complex task, right? How about here you have an image of a dog, right? Or a cat, for example. In this case you have if it's an image of a digit, it's fairly straightforward to have a label of 9, then you get a 9. But then how about more complex? When you want to encode higher level or more complex features in your training model, you would want to have a better model, obviously. So you have size variability, you have color information, you have complex features that might interfere with your learning algorithm. Definitely you can do more. So let me introduce you to this convolution operation. So if you are familiar with signal processing, you probably have if you are familiar with signal processing, you probably went through 1D convolution. So let me just give you an example of a 2D convolution. So here you have a kernel matrix and you have your input, and then for this example, so you're just making a sum product, you're just doing a sum product across the kernel matrix and your input. So 0 times 0 is 0, minus 1 times 105 is minus 105. Sum it all up, you get 210. Move the kernel matrix to the other side, then you get 89, right? Move that to the other side again, then you get 111. So this is how convolutional operation works. So what is actually involved in convolution? So first you have your kernels and filters. So this is your kernel matrix or filters, and then you have your inputs, which are images here, your input images, and then you have your feature maps as output. Here is your feature map, right? So, and then the input of a convolution operation can be prior feature maps. You're not restricted just images, you can also have feature maps to be an input of a convolution operation. Then the output will be another feature map. But then why do we do this? That's the question. So convolution is useful apparently to extract features, high level features. So this is a convolution operation to detect edges, for example. Here you have so you have the vertical edges, then you have the horizontal edges. This is a convolution operation to detect horizontal edges. So this is the output, and this is another output of the convolution operation. So convolution is useful for extracting features. But then who dictates what features to extract? So but then remember that before the deep learning revolution, I went through several techniques of feature extraction. Edge detection, you have histogram of oriented gradients. So prior to the deep learning revolution, what people do, what researchers does, is to extract those features manually using the SET algorithm. But then until 2012, there's a group of researchers from University of Toronto that shows the research community that it is inherently better to let the machine learning algorithm to extract the features rather than having traditional extracted features. The model will learn which features to extract. The model will learn what convolution operation to do. It dictate the floating points, it will dictate the numbers, it will dictate whether to extract edges or not, or even higher level dimension features. So this constitutes the era of deep learning. So here is the full picture of a learning algorithm, convolutional learning algorithm, convolutional neural networks. So you have convolution and non-linearity, and then you have max pooling. I didn't go through the concept of max pooling here, but then it's basically choosing the maximum value within a certain window. Then you have fully connected layers, and then you have a classification module. So first, basically what is happening here is you are extracting features from an image to get into a more higher level feature. You have here, then you decompose that, you just flatten it out into a fully into a vector, and then you have a feed that to a fully connected layer, and then classify them accordingly. So this is what the network can learn throughout the training process. As you can see, it may learn complex features such as edges or curves, right? And then along the way it will extract more complex features. So putting it all together, remember I went through this particular graph, particular animation of a linear regression problem, where you just go through the error curve downwards, using an algorithm called gradient descent. So in this case, you have parameters that you can modify. In this case, M and B, you have a loss function that you want to minimize. Then you frame the problem as a minimization problem. Now, in our case, in the case for convolutional neural networks, you have parameters to modify, which are the values of the convolutional kernels that dictates which features to extract. So remember, the values of the convolutional kernels can detect edges or detect curves. Now, in this case, values in the convolutional kernel may dictate what features to extract. So those are the parameters that you are modifying over the course of the training process. And then you have the loss functions that you want to minimize. Right? In this case, we have a novel classification loss, and then you just frame that as a minimization problem. So see how at every time step the dot moves closer and closer to the minimum. Here, going closer and closer to the minimum. So that constitutes the theoretical part of my workshop. So in this link, you will find a hands-on project or hands-on experiment that you can go through. It's very interesting. It's basically a food recommendation system, image-based food recommendation system using computer vision. So if you are following from home, you can go through this link to follow the hands-on session. So if you guys went through the link that I have given to you, you will be presented with this following view, which is basically a Google Drive. So you can go through the instructions to run to run the existing notebook or Colab notebook. So pretty sure you are familiar with Colab notebooks. It's basically a Python-based experiment environment for machine learning enthusiasts. So you can go through the instructions, but what I will do is just go through this particular notebook with you guys, and just go through the to the code and just to explain in a very high level and intuitive manner to you guys what is going on beyond the hood. So yeah, this is a collab notebook that I made to emulate how data scientists at Gojek use deep learning for their food recommendation system. So I'm pretty sure that you are you guys used a lot of food delivery services from time to time. You have Grab Food, and then Food Panda, and in our case in Jakarta in Indonesia, what they do is to deliver food using motorbikes, which is similar to how Grab Food and Food Panda operates, but this is a very big thing in Indonesia, and particularly in Jakarta. So Gojek uses deep learning for their food recommendation system. You can just view this particular YouTube video to understand more what is going on. But let me just go through several of the things that are highlighted in that particular video in this following notebook. So they are using a food dataset, food 10 dataset. It's basically a 100, I think it's a 10,000 or so images. You can see there's an image of lobster rolls and blah blah blah. Okay, let's make us go through this. Okay, yeah, so there's a lot of images basically spanning across different food classes. So first you go through the installations of the modules, and then you import the modules. So what I am using right now is Torch, PyTorch in particular. It's a deep learning framework, very useful for prototyping and even for production. I highly encourage you to learn PyTorch if you are very interested in deep learning, along with any auxiliary libraries. So these are some of the images. Image name, right? You have the lobster roll sandwich .jpg, then it's category 0, and then you have different categories. Obviously you have you have different categories, and 7, you have 1,000, and it's a fairly balanced data set. And then here we're just showing several of the images that we have within our data set. So you have a red velvet cake, you have oysters, you have raw oysters, and then you have sandwiches, so on and so forth. Pretty a lot of things here. You have onion rings, and you have fish and chips, pretty much any food imaginable. So in PyTorch, what you do is you wrap your data inside a dataset object. So in this case here, you have xtrain, xval, and all that. You just split it to a training and validation, and then for every iteration you will retrieve an entry within the dataset. So the dataset is like a dataset object in PyTorch is like a record. It's like a abstract record of what is in your dataset. So you can define your model here. So here you got self.layer 1, sequential, convolutional, blah blah blah. So you just define the sequence of your architectures. You are just defining your architecture. So see here, it's a 3x3 convolution, and outputting 16 feature maps with a kernel size of 5. It's an input size of 3, output size of 16, kernel size of 5, stride 1, padding 2, so on and so forth. Just go through this particular definition, and then forward we'll just define how it's laid out. And using your model, so this is the training loop. Remember that I went through the concept of epochs, iteration, so on and so forth. So you have different epochs. So for every epoch, he will go through every entry in your data set, and for, let's say, if the batch size is 40, then for every 40 samples in your data set, you will just go through that, and then you just call loss that backward to update your model parameters. And then if epoch, for every 5 epochs, what you do is just evaluate the models, and then here is the output. So you can see the loss will be reducing. If you were to run your own model, the loss will be reducing. And for after 1 epoch, the output would be the resulting accuracy is 38%. Then you can use also a pre-trained model. So pre-trained model is basically your model, but then it's a model that has been pre-trained on a much larger data set. In this case, it's called ImageNet dataset. Just go through that, prepare your pre-trained models, and then boom, you have an 81% accuracy. So pre-training helps when you have less time to train. So in a way, it shortens your training process, and then you have a much larger accuracy. So after the process, you have feature extraction, right? So I will not go through the feature extraction, but essentially what it does, what is being done under the hood is that you go through every image and then map them to an arbitrary vector. So let's say 1024 dimensional vectors in this case. So you extract the features, and then you reduce the dimension with PCA. So here PCA is a dimensionality reduction algorithm. So remember, you have an image, a big image for example, and then you squeeze them, you come up with a compact representation, in this case a 1024 dimensional vector, and then in the dimensionality reduction process, you reduce that particular vector further into 3-dimensional, for example, or 2-dimensional feature representation. The reason here is that we want to come up with a visualization of the model. So in this case, you see, after PCA, you reduce them into just 2 principal components, and then these are the feature representation after the PCA process. With TSNE is another, not really a dimensionality reduction algorithm, but it's a manifold generation process in a way. So these are the output of the images after TSNE. So for example here, let's just take an example of onion rings, the blue ones here, and fish and chips. See how they are clustered nearly together. Why is that so? Because they are inherently similar images. You can see back here, if I scroll up to the examples of the images that we have, onion rings and fish and chips are similar. So I hope that using that example, I can give you a brief overview of what feature extraction how feature extraction is actually being done in the context of convolutional neural networks. So you can see that here, what I do, if you are still interested, what I'm doing right now is just doing a clustering algorithm, and then see which images are similar. And then you can see here, interestingly, if you do a clustering algorithm, if you apply a clustering algorithm, you will see that similar images are clustered together. So in this example, you can see that here is an image of a red velvet cake, and then among that is a somehow is an image of a cocktail. Well, probably the learning algorithm kind of sees that these are similar images based on its own understanding. And here we have pretty similar images also. You have in this case you have salads, which are pretty much, it's very similar looking. You can see that it's it's kind of similar salads here, but then you have lobster salad here, and then the image is showing very similar features. You can see that there's a very messy looking diced up seafoods and stuff. So you can see that these are similar features which are from similar images. And there's here some another cluster, another similar images, lobster salads mostly. And then here you have the fried foods cluster. You have the fish and chips, and then you have the onion rings and whatnot. So yeah, so after that, I hope you guys have a better appreciation of what feature extraction is in the context of deep learning, especially for computer vision. I hope you enjoyed my part of the workshop. Stay tuned for other deep learning workshop series. Thank you. Have a good one.